Very good morning everyone. Today we'll start your first hardware experiment of your electromagnetic wave lab. This is your experiment 5, that is determination of voltage standing wave ratio VSWR and the reflection coefficient of transmission line or waveguide. Basically here we will take the waveguide. We will study this in your module 4 and 5, this waveguide. The equipments required are the Klystron power supply. All these things I will show you in the microwave test bench we have. Just see what are the things required. Klystron power supply. Actually a klystron is a microwave source which generates the microwave, and we need that power supply to generate the microwave. That's why we have a klystron power supply. Then we have VSWR meter which measures the VSWR. Then we have isolator, frequency meter, variable attenuator, slotted section, tunable probe, waveguide stand, match termination, BNC cable, and slide screw tuner. Then we will go to the next slide. So, what is actually a standing wave? Let us understand what is the concept of standing wave. Suppose we have a source. Suppose we have a microwave source. Then we have certain resistance. Then it is terminated with a load. Suppose the microwave is generated. Now you want to transmit it. This load can be, you imagine an antenna. You imagine an antenna as a load. So let us say the transmission line has characteristics impedance Z0. The transmission line has characteristic impedance Z0, and let us the antenna has the load ZL. For maximum power transfer, the Z0 should be equal to ZL. For perfect matching, your Z0 should be equal to ZL, so that whatever the incident wave we are sending, they will be transmitted by the antenna. But if ZL not equal to Z0, that means if there is mismatch in the characteristic impedance of the transmission line, characteristics impedance is Z0. If there is mismatching between Z0 and this is called the load impedance. So ideally ZL should be equal to Z0 for good transmission. But if there is a mismatch between Z0 and ZL, so the standing wave results. This is the incident wave. Right. If there is a mismatch between the incident wave, if there is a mismatch between ZL and Z0, a reflected wave is generated. You can see the some portion of the incident wave is reflected back. That means it back propagates. So there may be there is a interference between this incident wave and the reflected wave. So they superimpose. I can superimpose constructively, or they can superimpose destructively. What is called constructive interference? What is called destructive interference? Suppose you have this incident wave. This is going in this direction. If there is a constructive interference, then this crest will overlap with crest and trough will overlap with trough. So you get a maximum amplitude. Suppose the reflected wave is exactly in the same sequence of incident wave. Getting? The reflected wave is in the same phase, in the same phase of the incident wave. Then you can see this crest plus this crest, this trough, this trough. So they interfere constructively. So you will get a bigger amplitude of standing wave. You can see this plus this will result this one, this minus plus this minus result this one. So this is called the constructive interference. So what is a destructive interference? If the crest of the incident wave will overlap with the trough of the reflected wave. That means if there is a minus 180 degree phase shift, then the destructive interference will occur. You can see, suppose this is the crest and you will get a trough. This is the trough, you will get a crest. Getting? So this crest, this trough will cancel. This trough, this crest will cancel. So you will get a destructive interference. So you can see this example. This is the you can see the blue color light is the original signal. That means it's the incident wave, and this way the red color line is the reflected wave. Now due to the superimpose of incident and reflected wave, the standing wave is generated. The black color line is the standing wave. This is because of the mismatch of impedance, ZL not equal to Z0. You can see this is the incident wave. There is some mismatch in the load. Some portion of the wave is reflected back. So we get a standing wave. So today's class we will see this VSWR, standing wave ratio, and we will generate the standing wave and see. We will forcefully introduce a mismatch. First we will generate without any mismatch. That means we will try to match ZL equal to Z0. Then we intentionally introduce the mismatching by the slide screw tuner, by which we will intentionally introduce the mismatching, and we can see the low VSWR, medium VSWR, and high VSWR. So you can see first we will define the term what is called the reflection coefficient. The reflection coefficient is defined as reflected wave by incident wave. There is a derivation. There is a derivation of that. We will study in the class. This reflection coefficient is reflected wave by the incident wave. I have told you the incident wave and another wave is reflected back. So the ratio of the amplitude of the reflected wave and the incident wave will give you the called the reflection coefficient. And this is equal to ZL minus Z0 by ZL plus Z0, where ZL is the load impedance and Z0 is the characteristic impedance. Now you can also observe, if ZL equal to Z0, can you tell me what is the value of reflection coefficient? If ZL equal to Z0, this numerator is 0. If the numerator is 0, the rho value equal to 0. That means no reflection. Now it is proved that if load and the characteristic impedance matches, there is no reflection. And suppose, now let us see what is if there is mismatching. Suppose we take a short circuit line at the load and a open circuit line, what will happen to the reflection coefficient? Your reflection coefficient rho equal to ZL minus Z0 by ZL plus Z0. Now first case we have taken, if ZL equal to Z0, that means a perfect matching, rho equal to 0. Now suppose your load is a short circuit line. That means the load terminal, instead of ZL, it is short circuited. It is short circuited. That means ZL equal to 0. If ZL equal to 0, rho equal to 0 minus Z0 by 0 plus Z0. That is equal to minus 1. For a short circuit line, the reflection coefficient equal to minus 1. Suppose you have a open circuit line. For a open circuit line, this load is open circuited. For the open circuit line, Zn equal to infinity. Now put limit Zl tends to infinity, Zl minus Z0 by Zl plus Z0. Since the limit Zl equal to infinity, now let us divide the numerator and denominator by Zl. That means 1 minus Z0 by Zl by 1 plus Z0 by Zl. Since Zl tends to infinity, this term becomes 0, this term becomes 0. So the answer is rho equal to 1. So the reflection coefficient rho lies between minus 1 to plus 1. But the ideal value, the magnitude of reflection coefficient is lies between 0 to 1. So what is the ideal case? The ideal case is we want Zl should be equal to Z0. Our requirement is Zl should be equal to Z0. That means for ideal case, the reflection coefficient should be 0. That means there is no reflection. All the signals you have transmitted, all the signals you have sent will be transmitted. There will be no back propagation at the case and in the case of rho equal to 0. Then comes the term standing wave ratio, VSWR. Now we will try to establish a relation between reflection coefficient and the VSWR, voltage standing wave ratio. What is that? This standing wave ratio is defined as E max by E min. So this is incident wave plus reflected wave. The maximum value is during the interference of incident wave and the reflected wave. The addition is the E max and the subtraction is the E min. If I take EI as common, that is 1 plus ER by EI by, if I take EI common, 1 minus ER by EI. This EI cancels. So what is this thing? This is nothing but the reflection coefficient I have defined. That is reflected wave by incident wave. So this is what nothing but rho. So A is equal to 1 plus rho by 1 minus rho. So this is this one. So A is equal to 1 plus rho by 1 minus rho. Now if I take componendo and dividendo, that is S minus 1 by S plus 1. This is called the componendo and dividendo. Will be 1 plus rho minus 1 minus rho by 1 plus rho plus 1 minus rho. This is the componendo and dividendo you might have studied in your school. If you simplify this one, 1 plus rho minus 1 plus rho by 1 plus rho plus 1 minus rho. This rho cancels, this 1 cancels. This is 2 rho by 2. That means it is rho. So rho equal to, you have got that rho equal to S minus 1 by S plus 1. So this is the relation, rho equal to S minus 1 by S plus 1 and this one. So try to see the relationship. S is 1 plus rho by 1 minus rho, but rho equal to S minus 1 by S plus 1. Now can you tell me what is, you know the minimum values of rho and maximum values of rho. So can you tell me what is the minimum value of S? S will be, since rho equal to the minimum value magnitude, so S will be 1 plus 0 by 1 minus 0 equal to 1. So A start with 1, and if rho equal to, if you take rho equal to 1, then A is equal to 1 plus 1 by 1 minus 1. If you put rho equal to 1, it is 1 plus 1 by 1 minus 1. So 2 by 0 equal to infinity. So your standing wave ratio S lies between 1 to infinity. So the standing wave ratio lies between 1 to infinity, and the reflection coefficient lies between 0 to 1. So ideal case, for ideal case, the standing wave ratio should be 1. For good transmission, the standing wave ratio should be 1 and the reflection coefficient should be 0. Okay. So I will tell you the procedure for doing the experiment. These are the things required for your micro test bench setup. This is the Klystron power supply. I will show you in the lab micro test bench. This is the block diagram. I will show you each block diagrams. What is a Klystron power supply? What is a replace Klystron isolator frequency meter? We will go to that in the lab table. And this is the figure of all the instruments. So this is the figure of Klystron power supply. This is the replaced Klystron. This is the isolator. This is called the frequency meter. This is called the variable attenuator. This is called the slotted section. This is the SS tuner, slide screw tuner. This is the mass termination. This is the BNC cable we have used for CRO. This is called the tunable probe. This is the VSWR meter. Now let us go to the microwave test bench and see the demo, how we are doing the experiment.